just stay till the meeting ends. Fine. So here itself we had stopped in the morning class. I wanted to connect it back, but I couldn't do that. So here I had stopped, right? So we have seen two selection rules, spin selection rule and symmetry selection rule, or popularly which is known as Laporte selection rule, right? And the transitions which are symmetry or sorry spin as well as Laporte forbidden, say they will be almost, you can say that they are not at all taking place, or even if they are taking place, to very small extent they are taking place. So therefore corresponding lambda, this one epsilon value, it will be very less, it will be definitely less than 1 epsilon value, right? So that indicates that the species, it is not at all absorbing. But most of the DD transitions what we consider, they are spin allowed and Laporte relaxed. That is the better term that I should use, because if I speak strictly all DD transitions, they should be Laporte forbidden, strictly speaking. But there will be some relaxations, because relaxations to this rule, because of which to some extent these transitions they do take place, and with that some conclusion it can be drawn, definitely it can be drawn. And yeah, one more point here itself, if at all I have to mention, to observe this DD bands, usually we prepare the solution in higher concentration, like we go for say 10 raised to minus 1 molar concentration to that concentration, just 0.1 molar concentration we go with. You might be knowing, if you have recorded the organic compounds for that UV visible spectra, right, you prepare in 10 raised to minus 5 molar solution. It is because organic transitions, they will be allowed transitions, they will be Laporte allowed transition, their intensity will be high. So therefore in less concentration also you can detect them. But when it comes to DD, because these DD transitions, they are formally forbidden transitions, we need to have high concentration. Only in high concentration we can expect these transitions, that too because it is relaxed. So I was telling you this point, that relaxation, it can be because of various reasons. In octahedral complexes, usually these relaxations, they can be due to these two facts. One, the geometry of the complex, it will not be perfect octahedral, depending on the ligand, or say if the ligands they are different, if it is a heteroleptic complex, or because of geometry and deviation of geometry from perfect octahedral, all those things they affect this I, right? Inversion center, it will be affected, so that may relax the molecule from say inversion center, it may not be observed. In that case, that to some extent it relaxes this Laporte selection rule. And vibrations, there will be continuous vibrations, and because of these vibrations, mainly if you consider metal to ligand bonds, those vibrations, they also momentarily they change the I nature of inversion center, right? So they may remove inversion center for moment, and because of which this d orbitals, their parity, it may change. Parity means it's G and U, that is even called as parity. So that will be affected. Because of that, to some extent octahedral complexes they get relaxation, and transitions, DD transitions, they do take place. But still the epsilon value, it will be less in case of octahedral complexes. In general, if at all I have to say, it will be less, 1 to 100 range, right? So depending on the complex, maybe to the maximum, to this extent it can reach, otherwise it is usually very less. Whereas in tetrahedral complexes, if you can just refer to this epsilon value, this will be comparatively high, definitely this will be more than 100, right? And with this very high epsilon value, just by looking at the peak, it will be possible to say that the given complex, it is tetrahedral. Because if it is DD transition, somewhere, if at all I have to sketch it somewhere here, right? If this is the x-axis and if this is the y-axis, say DD transitions, they will be just like this, DD bands, something like this you get. So in the corresponding scale, if you draw say transitions which are due to tetrahedral complex, relatively say they will be like this, their intensity, it will be sufficiently high, because their epsilon values, it will be high. Say this is for tetrahedral complex and this is for octahedral complex, right? So the very nature of very high intensity of this transition, that itself shows that the complex, it must be tetrahedral, right? Why it is so? The reason for that, in case of tetrahedral complexes, if we go with this crystal field splitting itself, say E and T2, like this we can consider the splitting, right? So this E, it will form say ground energy level, and from this the transition has to take place to this T2. And the Laporte rule, it says, say if this is also G and this is also G, in that case it will be forbidden, right? But in case of tetrahedral complexes, maybe when we go for molecular orbital theory, you understand these things in a better way. So this E orbital, it will not be perfectly D orbital. Whatever we have as E orbital, since these orbitals, they are involved in sigma bonding. So in a molecular orbital theory, definitely you understand all these things in a better way. So therefore, this will be having D as well as P character. So therefore, we say that it is dp mixing. In this E orbital, there will be dp mixing. It will not be pure D orbital. There will be some P character. What I mean to say is metal p orbitals, they will also be involved in forming these e orbitals, right? And this T2, they will not involve in sigma bonding, so therefore they remain pure D. So now because of this dp mixing, if this was purely D, this was purely D, the transitions, they were totally forbidden. But because now this is a dp mixed orbital, some extent, to greater extent, not some extent, to greater extent, the tetrahedral complexes, they get relaxation from this Laporte rule, and that's how they show very high epsilon value compared to octahedral complexes. The best illustration, you can observe it in these two complexes, right? The next page, I have a diagram, pictures of this. See, this is CO2 plus octahedral complex, hexaaqua complex, or simply it is, say, COCl2, the counterion, it can be this one, Cl2. Just COCl2, cobalt chloride you have taken, you have dissolved it in water. What you get is pale pink color solution. And this pale pink color solution, it is because of formation of this species. All right. Okay. Next, to that itself, if you add some amount of HCl, immediately this water ligands, they will be replaced by chloride ligands, and this species it will be formed, right? Here it is CO, it is in 2 plus itself, but whenever the ligand it is chloride, there will be strong tendency for the formation of this complex. That's how this tetrahedral complex it will be formed. And this tetrahedral complex, it will be purple in coloration. Color wise, it will be, say, purple in the sense it's closely related to blue, that kind of coloration, right? And this one, I have said that is pink. One more term, two more terms that I have included. This will be pale pink. This will be pale pink. That indicates that intensity of absorption, or epsilon, it will be less for this. This is said to be intense. Intense means, so definitely more amount of energy or more amount of coolant that has been absorbed by this complex. Therefore, it will be intense purple, right? Okay, so those things we can see it here. If this is say COH2O 6 times 2 plus species, it will be pale pink, as you can see here. If you add concentrated HCl to it, readily it will be converted to this species, which is tetrahedral, COCl for 2 minus aqueous species, and that will be intense blue, right? Here, see, two questions definitely I need to answer. Okay, here I said it is pale, here I said intense. What is the reason? Someone can definitely speak out. Here I said it is pale, pale pink. Here I said it is intense. Just don't bother about this color now. Just concentrate on this. This is pale, this is intense. Why it is so?
Bands, DD bands.
Yeah.
DD bands.
In both the cases, these colorations, yeah, that is your assignment questions. In both the cases, the coloration, no doubt, it is due to DD bands itself.
For is tetrahedral.
Yes. As this is tetrahedral, what should happen to tetrahedral? Or what if it is tetrahedral?
Laporte allowed.
Yeah.
Allowed.
So
Laporte
here, to
allowed.
greater extent, this gets Laporte relaxation. So being tetrahedral, so this is to greater extent it is Laporte relaxed. So because of that, you can expect more transitions. As more transitions are taking place, definitely more amount of light it will be absorbed. That's how this appears intense. And we know that if it is appearing blue, definitely it is not absorbing blue color radiation. It is absorbing somewhere else, right? But the complementary color blue is being observed. But if you come here, pale coloration, this pale coloration, it is because of they are not that Laporte relaxed as compared to this, right? So less extent they are Laporte relaxed. So because of that, here intensity of absorption it will be less. This will appear pale. Now the second question that is to be answered in connection with this. So this is pink coloration, pink in color, and this one it is blue in coloration. How can this be explained?
The energy gap.
Yeah, it should be explained on the basis of energy, right? We know that octahedral complexes always the energy gap between say T2G and EG orbitals will be more, right? And whereas it comes to here, the energy gap between say, I'll write it like this itself, E and T2, this energy gap definitely it will be less, right? So now if you go with that wheel, or if I just I can just quickly draw that wheel. So for quick drawing, we prefer this kind of a star, which is known as David's star. Say I write it this way: violet, indigo I'll not consider, blue, green, VIBGYOR. Okay, like this. See now, if this is appearing blue, right? If this is appearing blue, your tetrahedral complex, it is absorbing orange, right? And if this is appearing pink, pink means it will be say, it will be close to red. It will be between somewhere say here in this region, it will be there. So therefore, say if I consider it to be red, it will be absorbing green. And see now, octahedral, it has much energy gap, and definitely our green radiation that corresponds to high energy, right? This is for octahedral absorption. Whereas tetrahedral, it is the energy gap, it is less. So therefore, what we can expect is less energy radiation is to be absorbed, and that's what you find. Orange, red, they can come at the other end of the series. Therefore, here it is less energy absorption. So therefore, this appears blue, and this is relatively more energy absorption. That's how it appears pink, right? Hope things are clear with this. Even in the
Vinay,
yeah.
hello, I didn't understand this less Laporte relaxed and Laporte relaxed.
See, this is octahedral complex, right? And this is tetrahedral complex. I'll just come to this slide. I said in case of octahedral complexes also, because of some reasons, Laporte selection rule, it is relaxed. In tetrahedral complexes also, to some extent, it is relaxed. But when we consider this tetrahedral complexes, right, always I can say that these E orbitals, they are DP mixed orbitals. They will not be purely D, they will be DP mixed, right? And these T2 orbitals, you can consider them to be purely D. So therefore, whatever transitions are possible here, they are not pure DD transitions, but they are from a DP mixed orbital to D. Our Laporte selection rule, it says D to D is formally forbidden, right? So, but this being DP mixed, right? Compared to DD transition, definitely this transition, it will be much more allowed. But if you come here, of course, what you can have is T2G and EG orbitals you will be having. T2G and EG orbitals you will be having, right? So here you can say that this T2G as well as EG orbitals, essentially they are D orbitals itself. But because of these reasons, say deviation from perfect octahedral geometry, or because of vibrations, to some extent here you will find relaxation, and that relaxation, whatever you get, that will be definitely less here, and here that relaxation, it is operative always, right? So therefore, tetrahedral complexes, always the transitions, they will be intense than compared to octahedral complexes. Is that fine now?
Yes. And one more doubt is there.
Yeah.
So if I is affected in octahedral complexes,
Yes.
so in that case, like it becomes so in that case it becomes ungirate. So again, it is ungirate to ungirate.
No, not like that. See, when we assign this G and U, whenever there is inversion center is present, with respect to that operation, if a orbital is chosen, how it transforms, based on that, we assign G and U, right? But now, when I is affected, I itself, you are removing, it's not there. In that case, for that moment, you cannot assign G and U parity to orbitals, right? So that makes these transitions allowed for some time, right?
Yes.
Yeah, fine. Right. So hope you have understood why this is pink, why this is blue, and definitely that should be correlated with the energy levels, right? That is fine. And this diagram, I have purposefully included it. In one of the examination, there was question, probably CSIR, when they had started this multiple choice question paper. At that time, they had released one model question paper. In that model question paper, if I'm not wrong, this question it was there, right? See, this is nothing but your silica gel. Maybe those who are from research background, definitely you must have seen it. This is silica gel, and nowadays this is used in desiccator as a drying agent. So earlier days it used to be calcium chloride, right? And nowadays calcium chloride definitely it will not be used, and instead of that silica gel it will be used. And the silica gel it performs same thing. It absorbs water molecules, but this silica gel essentially, if you consider, it will be white in coloration, or almost it will be colorless. But this silica gel it will be added with some amount of COCl2, right? COCl2 it will be mixed with silica gel, and that will be used in desiccator. Now, this COCl2, whenever you mix it with silica gel, essentially it will be COCl4 kind of tetrahedral complex, right? So, therefore, it will appear in this coloration, blue coloration. But what happens? It's very highly moisture sensitive. So, in desiccator, it starts absorbing water molecules, and when it starts absorbing water molecules, slowly it starts forming octahedral complex. This coloration, it is due to formation of this COCl4 2 minus kind of complex. But when it starts absorbing water molecules, readily this will be converted to this complex CO H2O 6 times 2 plus complex, right? So therefore, once the coloration it has completely changed to this, that indicates that silica gel it has absorbed sufficient amount of water molecules and it needs to be replaced, right? So just to get that indication when to replace the silica gel or when to reactivate, I should not say replace, it will be reactivated. What will be done is, once it will form this coloration, it will be taken off and it will be heated in oven, and it will form again blue color. It will be restored. That indicates that all water molecules have been evaporated, right? And again it can be used, right? So this is one of the application of this principle itself. Essentially, it is this principle itself. Once it is asked in CSIR net examination also, there is also a valid piece of information that each and every one of you should know. Therefore, I have said it, right? Yeah. So yeah, this is what I wanted to tell. Now I think we can go to questions, right? Right. First question, it was very, very simple. You need to be logically correct in all these questions. Definitely, you can understand the importance. You can find some 9 to 10 questions almost all year. You have one or the other question from this. Either it will be from selection rules or it will be from color of coordination complexes. So therefore, it's quite important thing. What they ask is that the complex that absorbs light of shortest wavelength. See, what they are asking is, it is shortest lambda. So shortest lambda, it refers to highest energy. This you should know, because energy it is inversely proportional to lambda wavelength, right? If it is highest energy, delta naught it should be high enough. And if delta naught it is to be high enough, ligand should be strong. This is the logical thing that should come to your mind. Strong ligand should be there, right? Now, if you just check all these things, everywhere it is CO3 plus octahedral complex. All options, they are CO3 plus octahedral complexes. And where they are differing, they are just differing in the ligands. If you know the exact position of all these ligands in spectrochemical series, this question it can be answered very straight away. Say F minus among the four is weakest. Next comes H2O, water, and next comes your oxalate, and lastly it is ammonia, right? Ammonia among the given ligands according to spectrochemical series, this itself is the strongest, and that's how you should go with this option. So I was checking your assignments. Many of you have gone with this oxalate option, maybe thinking that to be the stronger. But if you know the spectrochemical series, in general, I have said you, oxygen donors, they are weaker than nitrogen donors. Though this is chelating, this being oxygen donor, it is definitely weaker ligand than ammonia. Therefore, you should go with this option, option C. This was the correct answer for the question, right? Okay, now in detail I have discussed this, so I need not discuss this this fact again. So I think I should mute all once again, right? So this I have in detail I have discussed in both the cases, whether it is this complex or it is this complex. In both the cases, the transitions, they are DD transitions itself. Based on that itself, coloration has been explained. And of course, in this case, the LMCT, MLCT, we have not discussed it. Charge transfer transitions, CTs, they are not possible. CTs are not possible, right? And yeah, copper complexes usually they give CTs, but it is cobalt 3 plus, just for your information. Cobalt 3 plus it gives CT, charge transfer transitions, but CO2 2 plus usually it will not give this charge transfer transition. So therefore, with the cobalt 2 plus in both the cases, it's cobalt 2 plus. Of course, if you know that it is DD transitions, no doubt. Otherwise, also it is this answer itself, because CTs they are not possible. Right. This is one more question. Very simple one. You need to understand the things properly, right? So nickel complex, this is simply a nickel complex, Ni, where Ni is in 2 plus oxidation state, right? Some ligand L they have taken. They say that it shows 3 absorption bands, 8,500, 1,000, 15,400 and 26,000, right? Yeah, that is the characteristic feature of nickel 2 plus octahedral complexes. It will give 3 bands. So how it gives rise to 3 bands, and exactly how those can be named, all those things we'll see when we go to orgel diagrams. For time being, yes, nickel 2 plus, it gives 3 absorption bands. In L case, they say it is at 8,500, 15,400, 26,000. And in the L6 hash, dash, that is L dash, when ligand is L and when ligand is L dash, these are the two things they have given. The values, as you can see, it is definitely more than this, right? So 10,750, it is greater than 8,500, and 17,500, definitely it is greater than 15,400, and lastly this 26,000 band, it has shifted to 28,000 centimeter inverse, right? Just based on this, it should be possible for us to conclude that L dash is stronger ligand, because when we have stronger ligands, delta O it will be more, and the energy that is required for transition, it will be more, right? So L comparatively, compared to L dash, this is weaker ligand, right? So this is the proper logic that you are supposed to find out. Now, just search where this is appropriately matched. First ligand, it should be weak ligand. Second ligand, it should be relatively strong. That is there only in this option, right? Or even if you just know that water it is weaker than ammonia, readily you can go with this. But definitely, if you know the relative positions of all these ligands in spectrochemical series, definitely in that case also you can say that A is not the option, B is not the option, and C is not the option, right? But to do this, you should know spectrochemical series properly, right? So yeah, hydroxide and azide, if you take, definitely this hydroxide itself is stronger ligand, because azide you meet it along with this itself, halides itself, right? So there are good reasons why this N3 minus it is weak. So this is weak. This combination, no. And about this, at least you should know Cl minus and I minus. Cl minus itself is stronger. This is weaker, right? And here this is, if N donor, definitely this will be stronger. And here it is oxygen donor, so therefore it will be weaker. Even if you do not know about this, if you just know that this is strong, sorry, this is weak and this is strong, straight away you can say that option D is the answer for the question. Right? Okay. See, you can just analyze the situation. This is June 16 2 marks question. Relatively, I find this question difficult than this question. This was 4 marks question in June 11 examination. Just to tell you that year-wise the difficulty level, it is increasing so high that once which was asked for 4 marks, right? Now, in the future examinations, that may not even come for 2 marks. Right? 2 marks question, definitely they are far difficult than the earlier 4 marks questions. So therefore, you should understand how difficulty level of the exam is increasing, and you should prepare accordingly. It's not that if you are prepared for last examination that's sufficient. No, right? In future, definitely the question paper, it will be more difficult. Therefore, you should go one step ahead, right? Always your preparation, it should be in that way. Fine. This also, it has been discussed, right, in the morning itself while explaining selection rules, this has been explained. In MnH2O 6 times 2 plus, yes, no doubt it is spin forbidden. DD transitions here, both spin and orbital forbidden. This is the answer, right? But we are very sure that it is spin forbidden and it is perfect octahedral complex, in fact. And because of that, you will not get much relaxation in Laporte selection rule 2. So therefore, it is usually called as this complex. It is said that here both Laporte as well as spin selection rules they are forbidden. These transitions, DD transitions, are both forbidden, right? Option D is the answer. Right. Again, this is a question just like the earlier question. COL6 3 plus, it's octahedral complex of cobalt 3 plus. Again, COL6 L-6, octahedral complex of CO3 plus, right? This they say it is red in coloration, this they say green in coloration, right? Again, if I go with this star, right? Say I write it like this: violet, blue, G, Y, O, R. Say first complex L, they say it is red in coloration. If it is appearing red, so I should say L absorbs green. L absorbs here. L absorbs, or the complex where ligand is L, that absorbs here. So better I write it as L complex. Then next, the other complex they say it to be green. If it is green, the other complex, it is appearing green, that means it is absorbing red, right? So L dash complex, it absorbs this, it absorbs red, right? So that means L dash complex, it is absorbing less energy because red it corresponds to less energy radiation. And this L complex, if it is absorbing green, it is absorbing more energy. If this is the case, definitely L should be stronger ligand because it is absorbing the transition, it corresponds to high energy. L dash, it should be weak ligand. So this says that L, it is strong ligand, comparatively it is stronger, right? Whereas L dash, it is weaker. Just you search for that combination. First ligand should be stronger, second ligand should be weaker. That you can find here. Ammonia, definitely. Even in the earlier case, it was ammonia water combination itself, right? I think same question, it is asked in other way. I think this is June 14. So the earlier question, it was in June 16. See, again, same thing, it has happened, right? So question which was asked for 4 marks, that has been asked for 2 marks in 16 examination. Of course, they have changed it. The format of question, it has been changed, but the question, it has been repeated essentially. If you had understood the concepts behind this question properly, definitely that question, it could have been answered. Fine. Now here, if you check, so what we expect is that first ligand, it should be strong, the second ligand, it should be weak. That is the combination that we expect. But here, see, comparatively, right? Whatever I am writing here, it is comparatively. Again, don't claim that here ammonia I am calling it as strong, here I am calling it as weak. Here I am calling it as weak because it is in front of 1,10-phenanthroline, right? And here water and 1,10-phenanthroline, definitely water, it is weaker. This nitrogen donor chelating ligand, it should be stronger. And between water and ammonia, we know that water is weaker ligand and this is stronger ligand. So weak, strong, weak, strong, weak, strong. Only here it is strong and weak. Therefore, this option A. Right? Okay. So I would like to hear from you about this question because it's not that straight away. And definitely it is not that easy to predict also. But what I could find is that few of you, or many of you, or not many of you, at least few of you have answered this. I would like to hear from you what is the logic that you found here to answer this question. And one thing, say more than 50% of the students, they have confused this question for match the following kind. It's definitely not match the following kind of question. What they are asking is that among the following, correct combination of complex and its color, right? What they say is complex and its color, right? If they say complex and its color, it means that in which color does that complex appear. They are not again asking about absorption. They are appearing if they mention that its color, that means that in which color that complex is appearing, or essentially they are asking about complementary color, right? So like I would like to hear from you if you have any particular logic, of course, option C is the correct answer. But how you get to know that? Those who have done it correctly, just they can let me know their logic. Because what I could do is, definitely I can remove two options. But between A and C, it is not that easy to conclude, right? Okay, so first I'll tell you my logic based on which I have removed two options. Of course, I have removed three, but it's not very logical. It's not very logical to remove the third one, right? So, okay, I'll tell you. I have done again it on the basis of this complementary color star itself, right? So it is VBG YOR, right? And one thing that I'm very sure, I know about this COCl4 2 minus. I'm very sure that this is not the answer, because they say that COCl4 2 minus, it appears orange in color, right? And just now, or this is a very important complex, which is a tetrahedral complex, and it is it appears purple to blue. It's not definitely orange. So based on that, I know that this is not the answer, right? So just keeping this as reference, I'll try to find out the answer. What I do is I write it this way: absorbed radiation and emitted or complementary, right? Okay, first one, I know about this complex. Its color definitely I know. So therefore, this complex itself I consider. Sorry. Here I write COCl4 2 minus, right? So this appears in blue coloration, blue to purple, that I'm very sure. Based on that, what I can say is that it should absorb somewhere here orange, right? Then next species that I chose is this COF4 2 minus I choose. And no doubt this will also be tetrahedral complex, just like this itself. Of course, for that matter, all these four complexes what they have given, they are all tetrahedral complexes itself, right? Because CO2 plus D7, it has very strong tendency towards tetrahedral complexes due to high CFSE. Now, see, I found out that this absorbs somewhere orange here. COF4, whether do you expect this to absorb higher energy radiation than this or lesser energy radiation than COCl4 2 minus? That can be easily guessed. What do you think? Higher energy? I'm asking whether this absorbs higher energy radiation. I'm not asking higher wavelength. I'm asking energy. COCl here, chloride ligand, it is stronger ligand. Fluoride, it is yeah, your logic, it is correct. I'm sorry, Sandhya, what you had answered, it is correct. Cl, it is weaker ligand, and fluoride, definitely it is a stronger ligand. According to spectrochemicals, it is, yeah, fluoride, it is stronger ligand. So therefore, what I can expect is that, so this should absorb beyond, say, orange, higher energy radiation than orange it is to be absorbed. Say I go here, of course it goes difficult whether to go with Y or to go with B or to go with blue, it goes difficult. So just I consider that slightly this is stronger than chloride, so therefore say I go here. Let's say I find it to absorb this yellow radiation. If it absorbs yellow radiation, it would appear something like violet, right? But what they say is that COF4, they say it appears yellow. This is not definitely possible, right? See, because if it is appearing yellow, it would have been absorbed violet. And violet, definitely it is very high energy radiation. That much high energy radiation, we cannot just expect this complex to absorb. So based on this, I can just remove this option, right? And next one, what I do is I go with this COCN4 2 minus, and we know that this COCN4, CN, it is strongest, right? And because this CN ligand, it is strongest, so therefore correspondingly very high energy radiation it is to be absorbed. So out of available radiations, violet, it corresponds to high energy radiation, and if it absorbs violet radiation, it should appear yellow, right? But what they have given is, they say that it is given to be red, right? So therefore I can even discard this option, we are just left with this option. So in this way, I can say that, okay, this should be the logic. But the things are not that straightforward here, because we are just taking the guesses, and based on guess, we are coming to know that this is the answer, and definitely this matches, and this is the correct answer, and this matches with the given answer too. And so just in this way, if I remove these three options, definitely I can just say that option C should be the answer. So if you have followed any other logic, please let me know. Definitely, I know whatever the logic I have given, it's not that perfect logic, but this is what I can give. I don't have any other logic to answer this question. Maybe I should know the fact that the complex, it appears blue in coloration. That's how I should say that it is correct combination, right? Maybe to exactly answer this question, I need to know the color of all the complexes. Based on that itself, it is to be answered. Otherwise, if I want to trace a logic, maybe this I can give. Okay, now I would like to hear from you, because many of you have answered it. If you have any other logic, please let me know. Okay, so in that case, I assume that you have just taken a chance, and luckily it has got correct. Yes.
COCl for
COCl.
sir, I just guessed it like in the spectrochemical series.
Yes.
Cl just next to that NCS ligand.
Yeah.
So there won't be much difference in the absorption. As you are told, the COCl4 is blue color in the morning class.
Oh,
So I opted the NCS is blue color.
Okay. So that is the logic. Like compared to, yeah, if you know the color of this, definitely this is very far away. This is high energy, right? And yeah, in that way, I can say even this is close enough to Cl, right? Okay, that can be logic, but again, strong logic, I don't say that it's a strong logic. Fine, right? Okay, maybe I consider this question to be like you should knowledge based. You should know that CONCS 4 times that complex, it is blue in coloration. That is what finally I can say. All right. So this was the other 4 marks question, which was simple enough, right? Here it was match the following. And yeah, definitely we had not discussed anything about ML chart transfer and pi to pi star transitions. But still, even then, this question, it was manageable, because we know that in MnH2O6 times Cl2, the transitions, they are spin forbidden, right? Whereas in this case, it is spin allowed, right? DD transitions, they are spin allowed in this case. Just if I match these two, 2 I should go with C, 3 I should go with B. That is only one option, and therefore this should be the answer. And ultimately, 1 it matches with A. Yeah, and that is true. In iron porphyrin 9 complex, it is pi to pi star transitions that are usually possible, right? Okay, so therefore this option A. And last question was also easy, not that difficult. And many of you have got these 2 correct questions correct. Yeah, 3 complexes they have given. One thing about all these 3 complexes, all these complexes are octahedral complexes of CO3 plus. All these are CO3 plus octahedral complexes. Where the difference is coming, here it is fluoride ligand, here it is oxalate ligand, here it is ethylene diamine ligand, right? But CR, yeah. It's not CO, it is CR, right? And CR3 plus, it is D3 case, right? And you know, whatever is the nature of the ligand, it doesn't matter. All these D3 complexes, they will be high spin itself. All these complexes, they should be high spin, because this high spin, low spin here, if it matters, it's only for D4, D5, D6 and D7 case. Whereas D1, D2, D3, D8, D9, D10, you know that high spin, low spin, the ligand nature doesn't matter. So for all these 3 complexes, you can say that they will be T2G3 itself, and there will be 3 unpaired electrons. So based on that, their spin only magnetic moments are same. This statement I can easily confirm, right? And option C, or say statement C, 2 of them have optical isomers. And if you know the basics of isomerism, this is also true, right? So this can have optical isomerism, and even this can have optical isomerism. For these 2, optical isomers are possible. Whereas for this, no, right? This statement is correct. Third statement, all of them they show Jahn-Teller distortion. No, it is T2G3 evenly filled T2G orbitals. To have this Jahn-Teller distortion, we know either unevenly filled T2G or unevenly filled EG orbitals must be present. But this is evenly filled T2G orbitals. All of them they show Jahn-Teller distortion. Statement absolutely it is wrong. We can say that no complex it shows Jahn-Teller distortion. So we are very sure, even though we have not inspected EA, the statement A, right? Just with this, that is, it is possible to conclude the answer. B and C must be correct. So that is there here, and that is there here. And we are sure that D it is incorrect. Therefore, this cannot be the answer, and you should just go with A, right? And definitely A it is correct statement. The DD transitions, though you do not know their values, you can definitely match them. This is weak ligand. This is stronger than the earlier. This is further stronger than the earlier. So therefore, these values they should increase, and definitely it is there in the proper order. Therefore, this statement is also correct. A, B, C should be correct. Option A is the answer. Right? Yeah. These were the questions. Yeah, to take your doubts and to do these announcements, I'll just join back and stay back.